Welcome to Brain Vision.
Chapter 7, Problem 78. So we're given that we have a long ramp and its angle is theta, where theta is at 52 degrees. And we're given small blocks, and each of these blocks have a mass of 0.42 kilograms. And that they're set at rest at the above at the ramp at a height of h, which we don't know about yet. And we're given that in each case, the coefficient of static friction is small enough that the block starts to slide down the ramp as soon as they are released. This is important because it lets us know that kinetic friction is at action and these blocks are sliding. It says you are asked to find h so that each block will have a speed of 4 meters a second. So we know that our velocity is at 4 meters per second. At the bottom. Okay, and part A says, use work and energy considerations to find the required value of h if the block is made from cast iron, copper, and zinc. So the frictional coefficients for cast iron, mu's are 0.15. You can find this from the table below. Copper is 0.43. Zinc at 0.85. Okay, and so the first thing to consider is the energy from the system in the very beginning. So we know it was set at rest, so we have no kinetic energy. But because it's at a height relative to our reference at 0, we know that it has potential energy stored in gravity. So the initial energy is mgh. And our final energy. We know that the block at the very bottom of the ramp should have 4 meters per second squared. So all the energy is in kinetic energy. At 1/2 mv squared. Plus the work done due to friction. And so this work lost to friction is equal to the force of kinetic friction times the distance traveled. So we could solve for the distance traveled very quickly with some simple geometry. And so we have opposite over hypotenuse, h over d is equal to sine theta. And solving for d gives us d is equal to h over sine theta. Okay, and so now we just have to solve for a frictional force. So we know frictional force is the kinetic frictional force is equal to the coefficient of friction times the normal force. So we just have to solve for the normal force. So we'll finish writing this equation real quick. So we have 1/2 mv squared, the kinetic energy, plus mu n times h over sine theta. Okay, so in order to solve for the n, we need to solve for a force body diagram. And so we need to add up all the forces that contribute to accelerating this block. So we start off with the normal force, which is normal or perpendicular to the plane of incidence, the plane of the slope. We have the frictional force acting opposing the direction of movement. And we have gravity pulling this block down at mg. Okay, and so one thing we'd like to do is break up the forces into their components. But first we need to find out a coordinate system that would work best for this. And so in this case, we choose our y component to be in the direction parallel to the normal force, and the x to be in the direction of movement of the block. And so we can see that this theta matches this theta due to geometrical arguments. And so we want to solve for this normal force, so we can first begin by looking at the forces that sum up for the y. That sum the forces of the y. And this is equal to the acceleration of the block in the y direction. So we know this block isn't jumping off the ramp or flowing through, but it's following along this, so that the force in the y direction total of the block is equal to 0. And we know that the y component, since the normal's all in the y direction, is just n, and the y component of the gravity component, which is adjacent to the theta, so that makes it, and it's negative due to the pointing on the bottom, so it's negative mg cosine theta. Using this equation, we could easily solve for the normal force. We have n is equal to mg cosine theta. All right, so now that we have our normal force, we can plug it back into our equation here. And so we have 1/2 mv squared plus mu, where our n was mg cosine theta h sine. All right, and one thing to recognize about this, of why we are interested in the energy in the beginning and the energy at the end, is that we can set them equal to each other because of the conservation of energy. So we have that mgh is equal to the kinetic energy, which is 1/2 mv squared, plus the energy lost to friction, which is mu mg cosine theta over sine theta times h. And so we see that there's an h here and h here, so we can actually subtract both ends off to isolate h. So we have mgh minus mu mgh. And so one thing to recognize is cosine theta over sine theta is cotangent theta. And that's is set equal to 1/2 mv squared. So one thing to recognize about this equation, could it be done on the equation before, is that we have m across a whole entire board, so we can divide by m, getting rid of that. And so one thing we can do is isolate h. There's also a g on these two parts, so we can separate that. We have h times g times 1 minus mu cotangent theta, set equal to 1/2 v squared. With the final equation for h, we have h is equal to v squared over 2g times 1 minus mu cotangent theta. And there we have it. We have our final equation, and since we have all of our values here, theta, which you could plug into the cotangent, we have the mass, which we actually end up not using, and we have our mu values for each of the components and our velocity. We just plug them into this equation, and what we get for the height for the cast iron is an h value of 0.9, 0.92 meters. For the copper, we get an h of 1.23, meters. And so for zinc, we get an H of 2.4 meters. So one interesting thing to realize is as the coefficient of friction increases, as it does for these systems, or it goes from 0.15, 0.43, 0.85, is that we need to increase the height of this block that it starts from. And that makes sense. As we increase this, we're losing more energy to friction as all these other factors remain the same. And so in order to maintain a constant velocity, we need to increase our height. And so for part B, it asks, what are the required values of H for the copper block if the mass is doubled to 0.84? As we mentioned before, our equation doesn't depend on mass, so the height is actually the same. So it doesn't matter whether you double, triple, or half the block size, the value of H remains the same. For C, for a given block, if theta is increased while H is kept the same, does the speed V of the block at the bottom of the ramp increase, decrease, or stay the same? So one thing that we can use is this conservation of energy equation again. So H remains the same here. And so the only thing that's able to change is this theta and this V. And so as theta increases, we notice that as theta increases, sine theta gets larger as it approaches 90 degrees. And so as this gets larger and cosine theta gets smaller, this quantity gets smaller. As this is constant, if this quantity gets smaller, then this quantity has to get larger, which means as theta increases, so sine goes up, cosine goes down, so the overall quantity goes down, our V has to increase. So we have that as theta increases, our velocity, so as theta increases, our velocity increases as well. And that could be solved just looking at our energy.